Hello, ladies and gentlemen. Thank you very much, girls at the back, for all your help. Okay, so I'm going to be talking about the next iteration of the attitude controllers, and based on some of the questions earlier, I'm very happy to hear that there's a few people that are actually interested in that. How many people here have actually used ArduCopter and attempted to do tuning, used auto-tune? No? Nobody? Yeah, a couple? One? Okay, so not many people have actually... how many people here are familiar with PID controllers and that sort of thing? Same people put their hands up. Don't lie, Yanni. Okay, so I'll give a little bit of an overview of PID controllers. PID controllers are actually something that makes a lot of sense to everybody when they understand what they are. They're actually very simple things. PID controllers work on the concept of I am here, I want to be here, so therefore I need to move in that direction somehow. And we do that in, using a PID controller that's made up of the P, I and D term. The P term is the proportional term. That means that the correction, the strength of the correction, is proportional or based on the size of that error alone. The second term is the I term, the integral term. Now, what that tells us is that the reaction to try and close that error is based on how long that error has been there. So if that error is there for a long time, I gradually push harder and harder until I finally overcome what's stopping me from moving, and I move in to close the error to where I want to be. The final is the D term. The D term is the differential. Now the D term is based on how quickly I'm moving towards or away from the point I want to be. So if I'm standing here and I want to be on that spot there and I'm walking towards that spot and somebody pushes me from behind, I'm going to go and suddenly push back because all of a sudden I'm falling very quickly towards where this spot is. If I'm standing on this spot and I get a push in this direction, the D term, even though the error is really small, the D term will make me push back against it when somebody pushes me to the side. So the PID terms, it's a very natural and obvious way of dealing with a controller. So there are a number of things that allow us to make a PID controller work well. One of the most important things is how fast you're able to measure where you are versus where you want to be and react to that. If there is a large delay in my reaction time, then my PID terms need to be much smaller and much slower, and I get much sloppier control performance. So the speed is very important when we're talking about PID controllers. When we are building up our PID controllers, we have what we refer to as nested loops. Now that means we have one controller inside of another controller. In this case, we have our rate controllers, our rate of rotation controllers over here. And so that takes a commanded rate of rotation. So In this case, I want to move towards this spot this fast. So that's our rate controllers in angle. So I want to rotate towards this angle where I want to stop. Here we have the angle controller. The angle controller says I am this far away from where I want to be. So I want to move at a known rate towards this spot. All very obvious. So all this is doing is it's placing what we all do naturally when we move around the world into a mathematical representation that we can then run very quickly. Now, one of the interesting points here is the feed-forward term. The feed-forward term is actually something that's very important for our controllers. The feed-forward term lets us say that we know that we want to move in this direction and tell the rate controllers to move at that rate, while at the same time moving our desired angle. And in that way, we're able to actually keep this error term here for our angle 0, unless we have an external disturbance. And this simple little concept is actually one of the things that ArduCopter does extremely well and is responsible for one of the biggest things that allows us to handle big and small aircraft so much better than a lot of other controllers. So there are a number of things that we need to deal with when we are dealing with real systems. When we're dealing with simple systems without limits, the PID controller works very well. But this is the real world. And so we have limits to the amount of power that we're able to use to accelerate and decelerate our aircraft. And we need to deal with things like I-term build-up. So what happens when we need to close an error and we need twice as much power than we actually have? All of a sudden we've got a really big error here, and so we need 200% output to the motors. This is where we can have problems with I-term build-up. And we often see this when we're taking off from the ground. On the ground, if we're at a slope, the PID controllers are trying to level us and make us level. But because we're on the ground and the motors are all the way down, we can't do that. So the I-term is constantly getting bigger and bigger and bigger to try and lift that aircraft up and make that error 0. But we're not allowing the motors to actually give that force. So what happens when we increase the throttle and all of a sudden the motors are allowed to actually lift the aircraft as much as they like? So the I here is very big, and what happens is the aircraft flips over. So to stop that, we have a number of features that allow the motors to communicate with each level of the PID controllers and up through the navigation controllers and all of the other controllers that sit above this, so that when the motors are saturated, we deal with that saturation in the I-term. We may reset some parameters. We deal with it at the higher levels. We don't ask for a change in velocity or an increase in velocity in the navigation controllers. And so for you guys, when you're looking at our PID controllers and looking to implement your own version of these with a different type of controller, it's very important that you handle those saturation events so that the controllers above know when they're not going to get what they ask for. So when I want this angle and I can't have it, I need to know so I don't make silly decisions thinking that I will get that angle. So the way we structure our control loops, we have, for our attitude control, we have the user input from the pilot. So pilots tends to be very, well, most pilots anyway, don't tend to be very good pilots. So underneath that, we have an input shaping section. Now the input shaping takes the pilot's input and it turns a crappy pilot that's very rough and moves the sticks badly, not very smoothly. And it turns them into a wonderful pilot. It smooths the stick input like that pilot's been flying forever and has beautiful control over the sticks. The other thing it does is it does that knowing what the aircraft is capable of doing. So a small little racer, it's very agile, can twitch around very quickly. A large aircraft is much slower. So when you hold the sticks all the way to one side and let them go, the stick goes straight back very quickly. A small 250 quad, straight back. A big quad will lumber slowly too. And what this does is this knows what that quad is capable of, and so when it commands the PID controller and the feed forward terms, it does so in a way that it knows that the aircraft can actually handle. And in that way, it keeps those error terms small, and it ensures that the aircraft does not become unsettled and does not get into a point where the I terms are building up and the output of the motors are being saturated heavily. Okay, finally, the mechanical actuator. Now this is the output to the motors themselves. Now as these guys over here I'm sure will know, PID loops are assumed to have a very linear system, which means it's very simple. There's no change in like curved responses. There's no saturation. There's no sudden changes. So the mechanical actuator in that last loop, it takes care of those nasty things that real systems throw at us, and makes curved lines nice and straight so that the PID controller behaves ideally, as we expect it to, based on relatively simple maths. So, as far as the actual inputs goes and the types of controllers that we've got, at the top level we have an angle request, and that comes directly from our sticks if we're flying in stabilize, or this might come from our navigation controllers. It goes into our position controller. Now this is where we work out how far away from our desired angle we are, and from that we calculate a desired rate to close that angle. So if we're at 30 degrees and we want to be vertical at 0, we've got a 30-degree error. So we might have a 10 degrees per second rate that we request to close that error. So that's combined with our rate feed forward request. Now we know that although we want to be 0, we actually want to be slowly rolling to the left at say 5 degrees per second. So we will feed a 5 degree per second command into our rate request, and that will be combined with the correction, our angle correction rate request, and fed into the PID controller for the rates. And this is, I'll show you how this all breaks down in the actual, in a diagram in a second. Now finally, that comes down to the motor mixers. Now everybody knows a multi-rotor has multiple propellers, that you're adjusting the throttle on each propeller. And so this changes roll, pitch and yaw into each individual throttle outputs to the propellers of the multi-rotor. But it also does things like take into account the battery voltage and the limits of those outputs to linearize the system and to let the velocity controller know when it's asking too much. So the first little thing that is very important for dealing with that saturation problem that I talked about. So basic controls of multi-rotors are very simple. It's very easy to make an aircraft hover. Where it's difficult is dealing with aggressive flight, large disturbances, when you've been hit and you're upside down and you need to right yourself level again. Now in that situation, you've got a very large angle error. And this is like driving a car and stopping at the stoplights. Now if I'm 50 meters from the stoplights and I'm doing 50 kilometers per hour, I can stop very comfortably in the car, put the brakes on, no problems. If I'm 100 meters from the stoplights but doing 100 kilometers an hour, all of a sudden my passengers are getting very, very scared, because in order to stop, the distance it takes to stop with a constant acceleration is the square of the velocity. Now a PID loop assumes that the distance to stop is proportional to the velocity. So for small errors, everything's fine, everything's easy. But for bigger errors, you very quickly get to a point where your acceleration is more than what your aircraft can achieve. And that's where you get these massive overshoots and aircraft that flew perfectly well for a while, when all of a sudden they got disturbed, went boom, 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 and went into the ground. So this square root controller directly understands that there is a limit to how much correction an aircraft is able to provide, and it deals with that at the highest level. So this is a very simple diagram of our flight controllers. And if you're looking through the code, you'll see these various things. In here is the pilot input, or the navigation controller inputs. Randy pointed out the input function in one of the earlier talks. You know, Euler roll pitch, Euler rate yaw. So that's these inputs. Then we go through an input translation. Now this takes what could be very rough and ugly inputs from the pilot and turns them into sensible outputs for that aircraft, as if that pilot had been flying that aircraft for many years and was an expert pilot and knew exactly what the aircraft was capable of. And it comes out as rate requests. So angular rate requests. And from these commands, we work out exactly what angle the aircraft should be at and what rate the aircraft should be moving to. We then have two separate streams. One of them is that feed forward rate command I was talking about earlier. Theoretically, if everything was perfect, this would all be completely defining the pilot's input. But then here, we have the angular error components where the aircraft isn't quite where it should be. And these rates that are coming out here are to correct that small error. So that might be from a disturbance, it might be because you suddenly you're flying fast forwards and you've just tipped back a little bit forwards as the wind's caught you. Or it might be one of the motors have failed and you've got and you're dealing with a sudden loss of thrust on one corner. So the output of these two systems come into three rate requests: a roll, a pitch, and a yaw. What's that? So the rate controllers are simple PID, or reasonably simple PID loops. The difference that you might have noticed over what was, I didn't describe before, was this low pass filter. Now a PID loop is like a 3-band graphics equalizer on your sound card, on your audio system, on your speakers. The I term is your bass, that's your low frequency response. The P term is your mid-frequency responses. That does most of the work. Now the D term, I don't do high frequency very well.
You can try.
I can try. But the D term covers the high frequency. Now, if we leave the D term alone, the D term gets bigger and bigger and bigger the higher we go. And that can cause noise to get very, very strong in our system. So we always have a filter, a low pass filter, that stops D getting too large for the high frequencies. Now you notice a little bit of a difference between the roll, pitch, and the yaw. Now this is one of the other special little things that ArduPilot does that a lot of other flight controllers, DJI in particular, have not done well, or at least haven't done until recently. Now, yaw is very special. Everybody thinks of yaw as being one of the slowest controllers and weakest controllers. Funny enough, yaw is actually the strongest controller in a multi-rotor. Unlike roll and pitch and throttle, yaw has access to the full power of your aircraft immediately. In that when you increase your throttle, the torque on your motors instantly affects yaw. But for roll, pitch, and thrust, it takes time for that throttle to increase before roll, pitch, and thrust start to react. Whereas yaw, it's instant. And so this is like having a mechanically based D term. And so in ArduPilot, for most aircraft, in ArduCopter, we actually leave the D term 0. And we actually control that mechanical D term from the interaction of that system and the fact that we've got this inertia of the propellers and motors providing a mechanical determ, and I really apologise for the translators for this bit. So that's why this filter is out the front. So in yaw, the frequency of this filter does the same job as the D term for roll and pitch. So by increasing this filter frequency, we are effectively increasing the D term response of our system. And this is why our yaw is so much sharper and has so much more control than you'll see on most other autopilots. Although I think people are starting to work this out now, we're starting to see it creep in.
Leonard, was there some effect when, if you're looking like a slow motion on the arms and others, if you have a bad yaw?
So what Yanni was asking is how do we see that? So because of this mechanical D term and the speed at which yaw responds, we can't tune up yaw very high with a standard PID loop before we get oscillation. And people go, oh, we get this really bad yaw control. But what's happening is that it's actually oscillating at a high frequency on your arm. And so it's very sensitive to P. And if you place a camera down the arm and you increase it, you can actually see on some aircraft the whole arm is doing this as the motor speeds up and slows down very quickly. And it limits the amount of P term you can use in your rate loops. So when we design this correctly, we could increase the P term by 10 times over what the normal PID architectures could do with a very, very simple change. And it's very obvious too once you realise what's going on. It's not particularly clever. So, what's the problem with our PID loops? We're getting really good control, we can fly a whole range of aircraft, and we're very happy on that, and the people using our ArduPilot, once they've actually tuned them up correctly, are very happy with the response we can get. So how can we make this better? What are the problems that we're facing? The main problems are associated with noise, speed, and flexibility. We fly a whole range of aircraft, and each of these aircraft have subtly different requirements in how to best interface with those actuators and the control of the aircraft. So we want to create a system that's a little bit more flexible and also has more flexibility in the way that it handles noise, so that we can get closer to that optimal point of control. Okay, who here knows what aliasing is? Hey, anybody else? Okay. Aliasing is a very nasty problem with digital systems. What aliasing does is when you have when you're sampling a real signal is continuous. It moves smoothly. When you sample that, you have discrete points. It's not like this, it is like this. Now, with aliasing, what aliasing means is if you're sampling here and here and here, and you have a frequency, a movement that is faster than your sampling rate, it looks like a much lower frequency. So a signal like this, if I'm sampling here and here and here, looks like this. And so a high frequency noise can come down and look like low frequency movements of your airframe. And so an aircraft that should be dead still will do this, because this high frequency noise is tricking your aircraft into thinking that it's moving. And there's a number of ways we deal with that. And so that's what this is showing here. So for multi-rotors, blade passage frequency, where the propeller blade goes over the arm and hits the top of the arm, is a big source of this noise. And so with blade passage frequency, we have a big spike of noise, where this is frequency along the bottom axis. I should have labeled that. Yeah, I did. And so this is all of our normal movement, the stuff that we want to deal with. Then the orange here is our background noise that's always there in any system. And the red is caused by our propellers hitting the arm as the air comes down and hits the top of the arm. And we see these spikes in the frequency domain. This is like looking at the graphic equalizer of your stereo when you get the waterfall plot. Now, the first thing that helps stop this is the vibration isolation of your flight controller. You see there's a number of flight controllers out there that are starting to provide you with mechanical vibration isolation on the board. And if you're using one of the smaller flight controllers, you might build that into the system yourself. And what that does is, it's fantastic. It reduces all of that higher frequency vibration straight away before it gets to your sensor. Now we get to the nasty bit. This is where aliasing. This is the frequency with which we are sampling the system. After we sample it, we can't look at anything above the frequency that we're sampling. So all of this disappears. But what happens is this gets folded back down into this range. So we see our control reflected here and here, but we also see all of these large signals that's there and here. This one, that far across, mark the distance. And you can see that they've come right down into our control bandwidth. And this is nasty, this is bad. So, one of the ways we can address this is we move our sampling rate higher. We go from a 400 hertz or a 500 hertz sampling rates to a 1 kilohertz sampling rate. We go from 1 hertz to 400, we go 4 kilohertz to 8 kilohertz. We increase the sampling rate. Oops, I went wrong way. So now, you can see because my sampling rate is up here, this signal has appeared down here still, but this big, strong signal is a long way. So it's up at a higher frequency and out of my control bandwidth. Now that we've got it into a digital signal, we can now filter and we can now attenuate. We can make these signals weaker using filtering. So by filtering these out, as we move further away from the signals we're interested in, we can make them smaller. And you can see that these big signals now have been made much smaller. Now, another thing, that's with a simple low-pass filter. One of the other things we can do is we can use notch filters. Now, a notch filter takes a very specific frequency band and removes it. It takes that out. And so by placing a notch on this particular signal that's very close to the frequencies that we want to actually operate in, we can reduce that very small. Now, you can see here we're starting to get a very nice, clean representation of our original signal without the noise having a big impact on that shape. This is all just to explain. The real signals look a little different to these. These are just triangles representing where you might see strong spikes in your spectrum. And those spikes will move around depending on the RPM of your propellers, for example. But we're able to use these techniques to deal with these strong signals. So, there are a couple of things that we're doing in the new attitude controller design to improve the filtering and the flexibility of our controllers. So, one source of noise is the output of our EKF that is currently unfiltered. So we see a significant amount of noise coming through the EKF as our position estimate. And that's currently not filtered. And that's actually one of our significant sources of noise. We also want to be able to move the frequencies and sampling rates around in our system so that we're able to run the loops that we want to run very quickly, while the loops like the attitude control loop, the angle control loop, doesn't need to run as quickly. So we can save processor speed by reducing that rate, whereas our rate loops, we might want to run that at 8 kilohertz, very, very fast. And that's where enabling different update frequencies for the various parts of that loop that I talked about earlier comes in. So, this is the topology of the new rate controllers. To deal with the added filtering requirements, we are looking at a low-pass filter on the output of our angle, of our rate request, sorry. We have broken this filter into two separate filters instead of our current system where you can choose to have this filter here or here. This will allow us to take your control to a new level again, especially for very small, aggressive aircraft. Finally, on our IMU reads, we're actually adding notch filters to the IMU input, along with the second order low pass filter that's already there. So this filter rolls off and takes everything, rolls off slowly and takes all of the high frequency noise away, whereas this one allows us to target very narrow noise bands where we've got a blade passage frequency or some other very specific noise source.
How do you know what that frequency is to a notch?
Okay.
Is that flexible? Or?
Yes. So the way we do this, who knows what an FFT is? Yeah. So by recording the sensor data, we can do an FFT, which shows the spectrum of your signal. And that tells us where you're seeing your noise. And by recording a flight, you're able to show that at this throttle level, you see a strong noise at this frequency. As you go up in throttle, it moves up to here. So by placing a notch filter that will cover that range, you're able to attenuate the strongest and normal operating normal operating areas of your aircraft. We're also looking at providing a function that can automatically tune that notch filter up and down based on an FFT that's running in the background, so that it can track that if you know what type of noise, like blade passage frequency, that could be very useful. So the flexibility, that allows us to run different areas of this controller at different rates. Sorry, I apologize. So the flexibility side of things is dealing with different types of aircraft. For example, for aircraft that rely on a flapped output, like the tail of an aircraft. So a tail sitter, a plane that wants to take off like this and then fly forwards. That aircraft uses moving actuators on the rear surface. In order to control those well, you need the feed forward is the part of the controller that does most of the work. And so by setting up our system to output that separately as opposed to together the way it is at the moment, we're able to accommodate the requirements of a wider range of aircraft and control types. The flexibility here and how we use these filters is another component that allows us to tune the frequency response of our PID controllers to different aircraft. Okay. Finally is the update rate. We want to be able to separate the speed at which we input these commands to, say, 50 Hertz, while running this inner filter, the PID loop, at 8 kilohertz. But in order to maximize the effectiveness of these filters here, we may want to run our reads at 30 kilohertz to provide the maximum noise rejection of our system. So to do that, we need to take care of this low update rate that's going, whereas the rate loops are going. So what do you do with all those samples in between, where this is very slow, but this is running much faster? And so this slew box here joins those dots and turns that low rate signal into a smooth input into the rate controller. Adds a little bit of delay too, which isn't a good thing, but that's one of those trade-offs you need to make as an engineer. Finally, this is the other area that takes a big hit. Servos, we may only be able to output to a servo at 50 Hertz. But if we run this whole loop at 50 Hertz, all those noise components that you saw would all be right in that 50 Hertz bandwidth, and it would kill the system. So by running this at 400 Hertz in plane, for example, and then outputting only at 50 Hertz, we're able to keep those noise signals out of the servos. and make planes much more robust to engine noise, for petrol-driven engines and that sort of thing. So, thank you again for the translators.